Hello, in this video we're going to take a look at a year 2 rate question. The question is quite long, it's got a lot of information, so you might want to take photographs of the various tables and data as we go along. You will need a calculator, so make sure you got that handy, and paper. The format follows the same as usual, where red text is extra information, blue text is the model answer, what you should write, and black text is the question. The question is about orders of reaction, so you need to know how to work out orders of reaction from experimental data. You need to know what the rate equation is, the units associated with the rate constant, and also the Arrhenius equation. Let's take a look at the question. So pause the video, read the question and press play when you're ready for the first part. Okay, welcome back. So here we are just zooming in on the table. We still haven't been asked what the question is yet, but that's the data you need. So you might want to take a photograph of that. I'll give you the opportunity to do that if you want to pause it. Okay, so from this, it's a good idea to have an understanding of what rate actually is. We can think of the rate of reaction as a change in concentration divided by a change in time. So for P in experiment 1, we can see that the concentration has been reduced from 1.00 times 10 to the minus 2 moles per decimeter cubed to 0.92 times 10 to the minus 2 moles per decimeter cubed in the first 5 seconds. So we've got a change in concentration divided by a change in time. So if you've got, if you had the opportunities, you'll need that data to answer the first part of the question. So if you've got a photograph, or if not, now's the time to take a photograph of that. So we're asked to complete the table here to indicate the initial rates of reaction. It gives you what the rate of reaction is for experiment 1. So how have they arrived at that? Well, we talked about that previously. The change in concentration is given by the 1.00 times 10 to the minus 2 subtract the 0.92 times 10 to the minus 2. That's the change in concentration. Divided by 5, that's the change in time. So that's the initial rate of reaction for experiment 1. If we apply the same logic to the next two experiments, it gives us 3.2 times 10 to the minus 4 moles per decimeter cubed per second for each one of those. Okay, so that's the initial rates for experiments 2 and experiments 3, and I've used two significant figures, the same as they gave us in the question for experiment 1. Okay. So the next part of the question is asking us to determine the order of reaction with respect to P and the order of reaction with respect to Q. So I've abridged the information from experiments 1, 2 and 3, and I've also given us the rates of reaction. So that should be enough to enable you to do that. If you'd like to pause the video and press play when you're ready for the answer. Okay, so welcome back. The rate equation is going to be rate is equal to the rate constant K multiplied by the concentration of P raised to the power of X. In this case, X is the order of reaction with respect to P, multiplied by Q raised to the power of Y, where Y is the order of reaction with respect to Q. Okay, so we need to compare experiments. Now, one of them is a little bit easier than the other. If we take a look at experiments 1 and 2, the concentration of P is doubled, is multiplied by 2. Q remains the same and rate is doubled. So anything that's happened to the rate is solely due to changing the concentration of P. And as we double P, we double the rate. So that will be a first order reaction with respect to P, the concentration of P. A little bit trickier to find the order of reaction with respect to Q. I took a look at experiments 1 and 3. So P, the concentration of P is halved or times 0.5, and the concentration of Q is doubled and the rate is doubled. So if P stayed the same and Q was doubled, if rate was doubled, you'd expect it. If rate was doubled, that would be zero order. Well, that's not the case here. So we had to kind of combine the effect of what has happened to P. So if P is halved and it's first order, you'd expect the rate to halve. Okay, but the fact that it's doubled means that it's second order with respect to Q. Okay, so a little bit of a tricky one, that one, but very possible. So the answer to the question is it's first order with respect to the concentration of P, and it's second order with respect to the concentration of Q. Okay. Okay. So now we've got a different question. A reaction between substances R and S was second order with respect to R and second order with respect to S, and we're given a temperature. Read the question, pause it, and press play when you're ready for the answer. Okay, welcome back. So I've just abridged the question there. We know that rate is equal to the rate constant K multiplied by the concentration of R raised to the order with respect to R multiplied by the concentration of S raised to the power of the order of reaction with respect to S. So we simply need to rearrange this to make K the subject and put in the data which is given to us in the question. Once we do that, we get a value for what K is. It resolves to 19992. In order to work out the units, we know that the units for rate are always moles per decimeter cubed per second, and we know that the concentration units are moles per decimeter cubed. So we've got 1 mole per decimeter cubed term on the top, and we've got 4 mole per decimeter cubed terms on the bottom. So that's going to resolve to moles to the minus 3, decimeters to the 9, seconds to the minus 1. So K will always have units of a sort of a 3 to minus, a minus 1 to 3 ratio of moles to decimeter cubed. So it's either mole dm minus 3, mole squared dm minus 6, or in this case moles minus 3 dm 9. And it's always going to end in per second as well. Okay, so that's how we arrive at that. There's 1 mole per decimeter cubed term on the top and 4 mole per decimeter cubed term on the bottom of that expression. So that's how we get to the units for K in this case. Okay, so the next section, or the next part of this question, is about the Arrhenius equation. If you'd like to read the question, pause the video and press play when you're ready for the answer. Okay, welcome back. It's a good idea to know the Arrhenius equation. K, the rate constant, is equal to A, the pre-exponential factor, multiplied by e to the power of minus EA, the activation energy, divided by R, the ideal gas constant given to us in the question, multiplied by T, temperature. Now this is just a case of knowing the equations and also the correct units to use. I've used that rearrangement where I've taken natural logs. Another good one to memorise. That is at the format of a straight line graph. So if we were to plot ln k versus 1 over t on the x-axis, that would give us a straight line with gradient minus EA over R and intercept ln A. But we're not required to do that here. We just need to put the numbers in to get to find out what A is. In the next stage, I've just made ln A the subject because we are going to have to find A eventually, and the numbers from the question. So taking a natural log of K gave me minus 17.17941. You'll see that I've preserved a few additional significant figures there to ensure that I avoid any rounding errors. You may also notice, or you should also notice, that the activation energy, I've converted that into joules per mole to be consistent with the units. And finally, T I've converted into Kelvin, so 25 degrees Celsius becomes 298 Kelvin. That gave me the answer of 21.667 for ln A. So to do the inverse function of that, I find out that A is 2.57 times 10 to the power of 9. In terms of the units, top tip, the units for rate constant are always equal to the units for the pre-exponential factor. So that has got units of seconds to the -1. Please post any questions in the comments or email me if you don't understand anything or you'd like further explanation. Thanks for watching.